Okay, in the Desmos video, what we tried to show was that you could start with a very wacky looking function and pick any point you wanted to, and when you zoomed in, it would look linear. I just want to write out the conclusions of what we came up with. Now, so if we're at a point, and its x-coordinate is A, and its x-coordinate is B, we can estimate the slope of the line we see. Well, the slope of the line we see, we've been calling m, but the way we estimate it, it's just been with delta z over delta x. And the smaller the delta x gets, the better. Well, the idea is the partial derivative by definition is the limit of this kind of thing as delta x goes to 0. So what we're actually estimating when we're doing this estimate is the partial derivative of the function at that point. I'm going to write it all out with fx. So that's the slope we're actually estimating. So I can call it m if it's linear. It's the partial derivative with respect to x if it's not linear. If I do the y version instead, remember that normally we would call that n. And we're estimating this by delta z over delta y. And remember, the smaller delta y gets, the better. Well, the definition of the partial derivative is the limit of delta z over delta y. As long as you're going, due north, the smaller the delta y gets, the better. So when we're looking at this function that looks very linear and we're estimating n, what we're actually estimating is the partial derivative with respect to y. And the notation, you're going to see that with formulas, especially in mathematics, is going to be fy at ab. Now finally, if someone says, I want the equation of this, what we're using the z minus z naught equals m times x minus x naught plus n times y minus y naught. Now in practice, when we did that with linear functions, this gave us the equation of the plane. When we're actually zooming in and seeing it, it's not giving us the equation of the plane because the function is not a plane necessarily. What we're getting is the equation of the tangent plane. And let's just fill in what stuff is, right? Z naught is what you get when you plug in AB, right? So we would get z minus f of AB like that equals. M is the slope that was estimating the partial derivative. So what we're getting here is actually just the value of the partial derivative with respect to x, and this is going to be x minus a, like that. And then normally we would have n, but what n here is estimating the partial derivative with respect to y, and the smaller delta y gets, the better that estimate gets. So the plane we're actually looking at, and this really mirrors what we did in Calc 1, is fy ab times y minus b, like that. And what you're going to see here, this is a plane, right? Because FAB is a number, FXAB is a number, FYAB is a number, but it's the equation of the tangent plane. It is called the local linearization. They'll usually use the letters LXY for that. But it's the linear function that looks more like the graph or more like the contour diagram or more like the tables than any other linear function. And it's going to be very, very useful. But now we actually have a nice easy formula for finding the tangent plane of a function at a point.